Hey everybody, and welcome back to Quantum Mechanics for the Working Professional. This is another problem-solving session, and we're starting off Chapter 3 with the first problem of Chapter 3, which asks you to compute an expectation value. So, an expectation value of what? An expectation value of a general spin operator. So, recall that the spin of a particle can be represented as an operator, which we can use, therefore, to measure things, and it is given as a vector in three-dimensional space. That vector S has three components, right? Sx, Sy, and Sz. You might recall, of course, that those individual component operators are proportional to those Pauli matrices, right? So we can just, for completeness, we can write them all down here. And recall also that when we talk about directions, we're talking about directions in real space. That is to say, how we orient the magnet of the Stern-Gerlach device. So we mentioned that in the video. Let's talk about it more concretely right now. So that is to say, what is the orientation of our Stern-Gerlach device? Well, we specify that by picking a direction in space. So let's suppose that we have a vector v, a three-dimensional vector v, right? Given in components by, say, vx, vy, and vz. Just like that, only these vx, vy, and vz are just numbers. They're just the vector position, right, of how we're going to orient our device. Good. So to actually compute something, to actually measure something, to actually, let's say if we have our Stern-Gerlach machine ready to measure some silver atoms, either in the spin up or spin down direction, we have to specify, hey, that magnet's pointing in the z direction, or excuse me, the v direction. So that means that the operator of interest for us will be s sub z, which you can think of as v dot s vector. And we should normalize by the magnitude of v. So you can do this one of two ways. You can either divide out by the magnitude of v, right, which is v dot v square root, or you can just assume that the vector v is normalized. We'll just divide out here because I don't know, it might be useful later on, hint, hint. So let's compute the expectation value of this thing, right? So we're interested in the expectation value in a generic state of s sub z. So what is that? So that's psi v dot s over the magnitude of v psi, where once again, psi is a generic quantum state vector parameterized by two complex numbers, alpha and beta. Let's say alpha up plus beta down, where we're using the z components, right, for up and down, which we represent as a column vector. Let's just say alpha and beta. And so the bra psi is just what? That's just a row vector, alpha bar, beta bar, where the bars represent complex conjugates. Okay, good. So now we have enough to really compute this whole thing. So the expectation value of s sub v is given by alpha bar, beta bar, times this operator, whatever the heck it is, v over v magnitude dot s, which we know is going to be a 2 by 2 matrix, right? Because the s operators are 2 by 2 matrices, the Pauli matrices, times the vector a over b. So what remains to do is kind of, one, compute this thing as a vector, or excuse me, as a matrix, and two, finish this calculation. So let's do that. So v dot s is just going to be given by, now you got to go back up in the video and look at what sx, xy, and sz is. But if you work with it enough, hopefully you have been, it's like drilled in your brain, right? The Pauli matrices are a good thing to memorize. If you're going to memorize anything in quantum mechanics, memorize those. So the first component is vz. Similarly, the last component is minus vz. And then the upper right-hand component, what is that? That's vx plus minus ivy and vx plus ivy. The whole thing, of course, is multiplied by h bar over 2 times the magnitude of that vector v. Okay, awesome. We forgot to divide out. Nah, blah, blah, blah. Anyway, okay, good. So now we can actually compute this expectation value. It's the expectation value of the operator for a Stern-Gerlach device in a random direction or a specific direction that we choose, v, is given by alpha bar, beta bar, times this crazy matrix, vz, vx minus ivy, vx plus ivy, minus vz, times alpha beta, times this constant out in front. Okay, let's now proceed to do the calculation. All right, zoom up. Great. So this is alpha bar, beta bar, times a terrible, terrible mess. So let's go through it really quickly. That's alpha VZ plus beta Vx plus IVY, minus sign, sorry. Good, and then alpha times Vx plus IVY plus minus beta Vz times that terrible quantity out in front. Did I get all that right? Yes, good. So finally, one more calculation to do. I might even speed this whole thing up. So it's alpha mod squared Vz plus beta bar alpha Vx plus IVY plus alpha bar beta Vx minus IVY minus mod beta squared Vz, whole thing multiplied by this constant out in front, whatever. Okay, awesome. Couple things to point out here. First, everything is real. As we can see, the two diagonal terms are definitely real. You might notice that these cross terms here are complex conjugates of one another, and the complex conjugate, z, the complex conjugate of a complex number plus that complex number is equal to a real number, right? Because x plus iy plus x minus iy is just 2x. Okay, good. So let us proceed. And I swear I won't simplify this too much, just to say that's h bar over 2 times 1 over that magnitude squared, or excuse me, 1 over the magnitude of that vector times vz mod alpha squared mod beta squared plus, what is that? Alpha beta bar Vx plus IVY plus alpha bar beta Vx minus IVY. Okay, so that's the answer, by the way. So that's it. It's complicated. It's awful, but we're talking about putting a Stern-Gerlach device in a kind of a random orientation, so it's going to be, in principle, complicated. But I want to draw your attention to a few things. First, notice, because this is the physicist thing to do, by the way. If you're new to physics, if this is your first real physics course in a while, the way physicists tend to think is okay, how do I check my work? Let's look at extreme cases. Let's look at examples that I know for a fact. So looking at this answer, I see right away the coefficient of Vz, right, which is the familiar SZ operator, is just alpha mod squared minus beta mod squared, which we've done before. We've seen that in past problems. So we know that, for example, if alpha or beta equals 0, that is to say we're either in the spin up or spin down state in the z direction, that the cross terms would just go away. These other terms, poof, they're gone, right? And so that just leaves us with what we're familiar with. Similarly, if mod alpha squared is equal to mod beta squared, then that z direction, poof, is gone. And so we've been through this ad nauseum at this point. So hopefully you've been able to just confirm that this, in fact, is the answer. Good. Computing the variance is a whole nother game. I wouldn't necessarily wish that upon you, but it's actually not as bad as you think. But I'm not going to do that here. That's enough for now. Thanks so much for watching. Good luck with the rest of the exercises. I'll see you next time for problem 2.